Okay, we're recording. All right. So I will. So your exam is on Sunday at 10. You will get started at 10 o'clock, and you'll have 8 hours, and you'll upload it to where you receive it. Okay. Up to what I did yesterday. Anything else? I remind me if anything else I missed to say or I needed to say. Just had to put the phone on the charger. I believe I wanted to do an example to show you the full Z transform. Recall if we have an equal to something non-zero, if n bigger or equal to 0, and 0 if n less than 0, then the z of an is n equals 0 to infinity an z minus n, correct? Now, if an is defined, if an is defined for all n, that means it's not 0 for all n, then the z transform of an is n equal minus infinity to infinity an z minus n. Okay? So here is an example, and that example is in the book. That is example 3.9. Suppose we have un equal to a to power n, and this a to power n if n bigger or equal to 0, and it is a minus n if n less than 0. That's the absolute value of n. Then if you are trying to find un is n equal minus infinity to infinity of un z minus n. And that is n equal minus infinity. So if you're going to do it like this, to minus 1 to a minus n z minus n plus n equals 0 to infinity a to power n z minus n. Okay? And so this is n equal minus infinity to minus 1 a z to minus n plus n equals 0 to infinity a over z to power n. Okay? Now n equal minus infinity to minus 1, a z minus n is as az az minus n minus 1 so it's gonna be az n equal minus infinity to 0 az minus n, okay? And so this is az times 1 over 1 minus az, and this is provided az is less than 1. The same thing, n equals 0 to infinity of a over z to power n is 1 over 1 minus a over z, provided that a over z less than 1. Hence, z of un is this one plus that one is going to be az over 1 minus az plus 1 over 1 minus a over z, and for z here, for z less than a and 1 over a. This comes from here. This one and this one give you this one. Okay? So that is the z of un. So this is called double-sided z transform. Oh, actually, this is a, okay? All right. Okay. So let's go back to all right. Now we're gonna go back to what we were doing, the z transform, the convolution. Just give me a second. Okay. Convolution, back to convolution. Okay. Recall u star v, this is the convolution of u with v, is m equals 0 to n um vn minus m, and that is m equals 0 to n vn un minus n. They are the same. Okay. Delete. Now we have theorem 3.4.1. Okay? Lily, please. So if uz equal z of un, z equals z of vn, then the z transform of u star v is uz times vz. It's like the Laplace transform, the same thing with the Laplace transform. Did he stop? So here is the proof. Okay, so let's start from the definition. That is n equals 0 to infinity un star vn z minus n. Okay, but this is the same as n equals 0 to infinity, and this is m equals 0 to n um vn minus n. There we go. Okay. So, oh, I have z minus n. So I'm gonna rewrite this as n equals 0 to infinity, m equals 0 to n, un, sorry, um, vn minus m, z minus n, and this is the same as m equals 0 to infinity, m equal m to infinity, v n minus n, z minus n. So what I did is, this is rearranging the order of summation. Rearranging the order of summation. It's like changing the order of integration. Now we are going to set n minus k, n minus m equal to k. So then we have d of u star v equal to m equals 0 to infinity, k equals 0 to infinity, vk, z minus n will be minus m minus k. Minus m minus k. Okay? And this is basically m equals 0 to infinity z minus m times k equals 0 to infinity z minus k, and that is uz vz. Okay? All right? Hi, baby daddy. So this is the convolution theorem. Okay, so let's do an example. This is 3.10. Compute z of m equals 0 to n a to power m. Okay? Well, that is a little bit kind of fishy how to do that, because this is the sum of 1 plus a squared plus a n. So that will be 1 plus a squared all the way plus a to power n. And you're going to find the z transform of that. So what are you going to do? Find the z transform of each term? Well, what we're going to do is we're going to note that m equals 0 to n a to power n is 1 star a to power n. You see that? Okay. So if you take v equal 1 and u equal a to power n, you see what I mean? All right. So hence, by theorem, the one we just did, 3.41, we have z of m equals 0 a n to a power n is z of 1 or 1 star a n, but that is z of 1 times z of a n. Okay? What is z of 1? This is z over z minus 1 times z over z minus a. And z is bigger than the max of 1 and a. Okay? There we go. So we did it. So take a look about it for a second. I'll be right back. Any questions? All right, let's I am going to skip example 3.11. Please read example 3.11. Okay? Just calculations. Now, so let's take a look at some engineering application. Okay? A system is an abstract object that accept input signals and respond by producing output signal. Okay? And then in the book, I look at an example of, for example, if you have xn, that is an input, and this is your system, and then you get yn as an output. So in the book here below, if you read it, I describe such systems. Okay? Now suppose xan equal an equal to the function, the impulse function delta n. So we have impulse response hn. Okay? So for arbitrary signal xn, we have, recall this, we did this, an is k equal minus infinity to infinity, ak delta k of n. Remember how this is a shift. Look how we define delta k of n. Now the response to k equal minus infinity to infinity xn del k of n is yn equal to k equal minus infinity to infinity xn hn minus k.
Hey, Professor,
Yeah,
Is there any way you could rotate that board? Got a glare from your front door, I think. Oh yeah, that's perfect. You a little bit too far now, I think. You just rotate it. Actually, yeah, that's better. That's better. We good.
yeah. Whatever I do, it's not the front door. I think it's some of the windows. Yeah, it's maybe this thing on the front door. Does it go away? No, right? Is that any better?
Yeah, that's better.
All right. Yeah, look at it. Yeah, I can see the front door everywhere. That's not any better. All right. So this is the two-sided convolution. And this one is xn star hn, two-sided convolution. Okay? So let's take a look at an example. So suppose xn is 1, 4, 0, less or equal to n, less or equal to 4, and 0 otherwise. That means for n bigger than 4, for n less than 0. And impulse response, so this is input. And we have output, impulse output of an impulse response hn equal to 1 for 0 less or equal to n less or equal to 4 and 0 otherwise. So the output is yn equal xn star with hn. And that is k equal minus infinity to infinity of xk x of n, h of n minus k. Well, this is only valid, this is only good from k equals 0 to 4 xk hn minus k, right? Okay. So let's take a look at it again. This is xn. So in other words, I have yn equal k equals 0 to 4 xk h n minus k. So for n equals 0, y0 is, for n equals 0, is k equals 0 to 4 xk, no, what is it? Xk, for n equals 0, oh, for n equals 0, this is up to Oh, no, no, no. Here. For n equals 0, because remember, this is 0 to 0. Okay? Okay, let's, to be honest with you, let's us write it k equals 0 to n. I was trying to be more specific. So this is to n. Okay? So for n equals 0, you see it's 0 here. Xk h of minus k, that is x0, h0. Well, what is x of 0? That is 1 times 1, and that is 1. Okay? For n equal 1, y1 equal k equals 0 to 1, xk h1 minus k. Okay? So again, that is x0 h of 1 plus x of 1 h of 0. Because when k equal 1, this will be h of 0. So that is 1 plus 1, that is 2. Okay? Um, and then you can get the rest of them. And so you can get y2, y3, y4, and then you can get actually so many of them. For example, if you want y5, that is k equals 0 to 5 xk h of n 5 minus k. You see that? And that is x of 0 h of 5 plus x of 1 h of what? 4 plus x of 2 h of 3 plus x 0, 1, 2 plus x of 3 h of 2 plus x of 4 h of 1, and the rest are 0. Because if you go to h5, x5 is going to be 0. So what this is 0 plus 1 plus 1 plus 1 plus 1. And that is 5. Okay? So up to what? What is 5 minus number will give you a number bigger than 5? What is it? Because h or here, I mean, what is this n is gonna be? Okay, so you will get some values. So this is gonna be up to y8, and after that, I need you to show that y8 is 1. Okay, and then yn equals 0 for n bigger or equal to 9. Okay? Well, if you do y8, k equals 0 to 8 will be x1, x2, will be 8 here. That will be 0. You see? And then, so you go down, so you're only gonna get one entry. Okay? And that entry, where does it come from? It's gonna come from x4, and anything else is not gonna work. All right. So you can compute all this stuff, and then you will get that. Okay. Any questions? So you don't need to stop at n equal 4. I mean, this is a dummy variable. You know what I mean? Because you get the n minus k. Don't be, because that always contribute. Okay? So because this is 4, this is the most is 4, and from here you're gonna get 4. So basically it will be 8 minus 4 will be 4. So you have to go all the way up to 8. You see what I mean? And then after that will be all 0, because if you put 9 will be 9, but the biggest k can be is 4. And then because from here there will be 0, so it will be 9 minus 4, that will be y5, and so forth. Okay. Now let's take a look at another concept. So this is basically how you compute the convolution of two sequences. You know what I mean? Okay. Let yn be the output system. Then yn is k equal minus infinity to infinity xn hn minus k. Okay, h is the response. So you have input, response, output. Okay. Now then, the system is causal if and only if hn equals 0 for all n. For all n less than 0. Okay? So this is a definition by itself. Like the system we had before was causal. this system was causal because it was zero. Otherwise, that means for n less than zero. So this is a causal system. All right, but in some cases, it's not. So take a look at it. I'll be right back to get a drink water. All right. All right. Suppose the input signal xn is bounded. That is, there is a positive constant d such that the absolute value of xn less or equal to d for all n. Then yn equal to k equal minus infinity to infinity xk hn minus k. Okay? That is less or equal to k equal minus infinity to infinity xk h n minus k. Well, xk is less or equal to d. So this is less or equal to d, k equal minus infinity to infinity h n minus k. And remember what h is. This is the response of the system. So this, hence, yn is bounded if this hn minus k is bounded, converges absolutely, hn minus k. Thus, the system is stable. This is just a definition, a word, if and only if and only if k equal minus infinity to infinity h of k is finite, converges. And okay. So this is where we are now. And you can easily see that the previous system is stable. Why? Because h is between, it's almost 1. So that system is stable. Okay? For example, if we have, for example, xn equal to 1, for all n, I don't care, and for all n, let's say, and hn equal to 2 to power n for n bigger or equal to 0. So that is not stable. Not stable. Why? Because first of all, xn is equal to 1. So that is your constant d. So it's bounded. On the other hand, k equal minus infinity to infinity, hk is k equals 0 to infinity 2 to power k. And that does not converge. So this is not bounded. It's 2 to power k, and you're summing from k equals 0 to infinity. Okay? How would you know that this is not bounded? Remember, this is the lim as n goes to infinity of k equals 0 to n 2 to power k. Let's call it n minus 1. And that is the lim as n goes to infinity 2 to power k over 2 minus 1 or k equals 0 to k equal n. And that is the lim as n goes to infinity. This will be 2 to the n minus 1, and that goes to infinity. You see that? Okay? All right, let's take 5 minutes break and we'll come back. I'll be right back. All right, any questions so far? So there is another example. And this is similar to that one. Another example. This is 3.13. Suppose the input xn is bounded. Let hn, the response, the impulse response, is 0 for n less than 0, and alpha to power n for n bigger or equal to 0. So we would like to see if this system is bounded, is stable. Is the system stable? Okay. Well, we need to look at k equal minus infinity to infinity of hk, that is k equals 0 to infinity alpha n, alpha k, sorry. All right. And again, that is the limit as n goes to infinity of k equals 0 to n alpha k, let's say n minus 1. And we know this is the limit as n goes to infinity of alpha to the k over alpha minus 1 from k equals 0 to k equal n. And that is 1 over alpha minus 1, the limit as n goes to infinity of alpha n minus 1. If you put k equals 0, you get 1. All right? And that is infinity if alpha is bigger than 1, and 1 over 1 minus alpha if alpha less than 1. This is bigger or equal to 1. Sorry. So, hence, the system is stable if and only if alpha is less than 1. Okay? Any questions? All right, so that's enough of that. Let's try another pen. Okay, now we're gonna start a new concept. So this is section 3.5, inverse Z transform. Okay. Well, definition, the inverse Z transform. Let AZ be the Z transform of AN. That is V of AN equal AZ. Then the Z inverse of AN denoted by Z inverse of AZ is AN equals Z inverse of AZ. Okay? Then the Z inverse AN denoted by VN is AN equals Z inverse of AZ. So it's now how we compute it. Okay? So AN can be computed or found by different method, or may I say suitable method, such as inspection. That means we're good at it. 2, direct division, or we call it long-term division, partial fraction, 4, residues, and so forth. They're in the book. Okay? So basically now we're gonna go back. You are given the Z transform. What is the original sequence? This is the question now. How do you recover the original sequence? Okay? Any questions? So example 3.14, find AN where AZ is 1 plus 1/3 Z minus 1 plus 1/9 Z minus 2 plus 1/27 Z minus 3 plus. Okay? Well, we notice that AZ is 1/3 to power n times Z minus n summation from n equals 0 to infinity, isn't it? And recall what is the Z transform. And so we see that AN is 1/3 to power n for n bigger or equal to 0. Okay, so we did recover AN. Any questions? Example 3.15. Let's say we know find AN where AZ equal to Z squared over Z minus 1 squared. Okay? Let us write, so we're gonna rewrite AZ as Z minus 1 minus 2 over Z minus 2. I can do that, right? And that is Z minus 1 over Z minus 2. And that is 1 minus 1 over Z minus 2. Okay? Well, how good is that? Well, we're going to use some form of the binomial theorem. So we're going to use 1 minus x to power minus n as 1 plus nx plus n plus 1 over 2 factorial x squared plus n plus 1 n plus 2 over 3 factorial x cubed and plus. Hence, AZ is 1 minus 1 over Z minus 2. So N is minus 2. Is 1. Okay. So 1 minus X. All right. So this is going to be 1 plus 2 Z minus 1 plus 3 Z minus 2 plus 4 Z minus 3. So that is equal to N equals 0, infinity, N plus 1, Z minus N. Okay? So just replace N by 2. Will be 1 plus 2X, but X is Z minus 1 plus N times N plus 1. So this is 1 plus N 2. 2 times 2 plus 1 over 2 factorial. That will give you 3, Z minus 2, and so forth. And so if this is N equals 0 to infinity, AN Z minus N implies AN is N plus 1. Okay? Any questions? So you see how we did it. So you need to memorize, maybe this is an important formula from the binomial theorem. Okay? So and so forth. All right. Any questions? This is like a long-term division anyway. Okay. Let us try one more example. Let's try one more example. Find AN when AZ is 2 plus 3Z over Z minus 1 plus Z over 5Z minus 1. So now we know that AN is the inverse of AZ. And that is Z inverse of 2 plus Z inverse of 3Z over Z minus 1 plus Z inverse of Z over 5Z minus 1. Okay? Now let's try. Z inverse of 2 is 2 Z inverse of 1. What is Z of 1? That is 2 delta n. Okay? Go back to the table. There is a table in the book. Plus, we did this one. We proved this one. Z of 1 is 2 delta n. Now, Z inverse of 3Z over Z minus 1 is a 3 Z inverse Z over Z minus 1. And then that is 3 U of n. That is the unit step function. Okay? And now we are left with Z inverse of Z over 5Z minus 1. That is the inverse of Z over 5 will be Z minus 1 over 5. Okay? And that is 1/5 Z inverse of Z over Z minus 1 over 5. And we know that this is 5 times 1 over 5 to power n. And that is 1 over 5 to power n plus 1. Okay? Hence, an is Z inverse of AZ, and that is 2 delta n plus 3 un plus 1/5 n plus 1. Okay, there we go. Whew. Any questions? So this, I'm gonna stop here. I'm really tired and it's Thursday. And I will put the video up. Hopefully I will look at your homework today, third homework, and go from there. If you have any questions, you can email me, okay? From now to Sunday.
Yeah,
All right.
are you going to put any announcement for the final, because for the midterm? Sorry, so I didn't see anything yet.
Okay, yes, I did not. I will do it today. I will do it now immediately.
All right, thank you.
Okay. Any other questions?
So how many questions we're expecting to solve in the exam?
99 only. It's a joke. I mean, I answer based on the question. How's that? Don't worry about it. I'm a professor. I know how to weigh an exam and make sure. The exam supposedly is going to be given over 2 hours, okay? So it's like a 2 hours worth exam, all right?
Okay, all right, got it.
I'm being so generous, letting you open book, open notes, and 8 hours, okay?
That sounds good. Thank
Yes,
you.
don't worry. It's not the 99 questions, but all right. Any other questions? Other questions? All right. So the Z transform is really important in engineering. This the Z inverse is really important in circuits when you have a poles. I don't know if some of you are familiar with that. Like electric circuit 2, I believe, or something you will encounter, stuff like that, with the residue in it and so forth. So anyway, so this is where we are now. And I'm gonna log out, and you will hear from me today in an announcement, and after that on Sunday. Okay? All right, I'm gonna stop recording.